Now that we know the mathematical foundations of transforms, let's get a little bit more philosophical. Let's say that station and there's a platform and there are two trains, one train on each side of the platform. And you are sitting right here looking out the window. And then all of a sudden you see that this train is moving backwards. What's happening? Is it really that this train is moving backwards? Or is it really that you are the one moving forward? Obviously, when you have 2 points, A and B, you can have the same relative motion if B moves in some direction, or if B stays the same and A moves in the opposite direction. Okay? The same is true for transforms. Let's take a look at what that means. Let's say we have a coordinate frame A and a point P undergoing a transform T. So P nu is T times P. So far, means the following. There's some other coordinate frame B. The transform from A to B is T. I'm observing the point P in coordinate frame B. I multiply those two, and I get the location of P in coordinate frame A, which is perfectly valid, of course. One way to think of this is, look, I start off with my vantage point and coordinate frame A. I move to coordinate frame B, and from there, I observe point P. So I've moved from A to B. The difference was transform T, and from there, I've observed point P. Okay? But there's another way of looking at the exact same relationship. I start off with the point P in my coordinate frame A, and then it's actually point P that moves and gets to a new location. So in this case, P nu is the new location of P. And you can tell that P nu is the same in both cases. So again, in this case, I am moving from A to B, and from B, I'm observing point P. Here, point P is in my initial coordinate frame, and it's point P that's moving. Here, it's my reference frame that's moving. Here, it's the which of those two is the correct way of looking at this relationship? They are both correct. Okay? They're just, right, you don't know which one is moving. Maybe your reference frame is moving, or maybe what you are observing is moving. Both of those are correct. And there are situations in which you'd use both of these ways of thinking about the problem. So let's say that we have the following two questions. In the first situation, we have a camera that's mounted on the robot arm. The camera observes point P in its own coordinate frame, but then the transform from the world to the camera is T. What's the position of the point in the world coordinate frame? Well, the answer here is, as we've seen so far, T times P. Okay? But here's a different way of looking at the problem. We have a robot that is at location P in our world frame. The robot moves by translation T expressed in the world frame. What's the new position of the robot? Also TP. Okay? So we have the same relationship is the answer to two different problems. So fundamentally, the thing to remember here is that transforms can mean two things. A transform can mean that your vantage point is changing, that your reference point is changing. You're looking at the same thing, but from a different reference point. And you encode that using transforms, right? Here, we are looking at the exact same point P, but instead of looking at it from point A, we move to point B, and we observe it from point B. The point stays the same. Our reference frame has changed. In this case, our reference frame stays the same, but it's what we're looking at that has actually moved. Both of these are very important in robotics. We run into both of these problems. These are just two very simple examples of it. And transforms are used to encode both of these things. And again, it makes sense that the expression used in both of these cases is the same. Whether it's what I'm observing that has moved, or it's just my vantage point that has changed, you cannot tell that. That's the same thing. The relative motion is the same. So it makes sense that we have the same relationship in both cases. Let's look at another example of this. Let's say we have three transforms. And I'm going to use 2D for this example. This is my first transform. This is my second transform. And a third transform. And then finally a point P. Okay? What's the meaning of the expression T3, T2, T1, P? Well, there are two ways of looking at this. Is it the point that's moving, or is it our vantage point? Okay, let's think first about the case where it's our vantage point that's moving. And when we do that, we are going to go through this relationship from left to right. We start with the identity, our undisturbed original base coordinate frame. Then we get to T3. T3 is the identity rotation, so we're not rotating our axes, but we are translating by 2 units along y. So after doing that, our vantage point has moved up here. Okay, then we get to T2. T2 has no translation, but it has a rotation, which if we look at it, we realize x is pointing along negative y is pointing along negative x. We are rotating our axes 180 degrees around z. So after we've done T2, our vantage point now looks like this. Then we get to T1. Okay, T1 has, again, no rotation. We're leaving the axis unchanged. We are moving by 2 units along x, but careful. We are moving along the new x. Our vantage point has changed, right? So now our x is pointing in this direction, so we are moving by 2 units in that direction. So now, having done T3, T2, T1, this is our new vantage point. So now let's look at point P. but it's point P expressed in this new vantage point. That is the point P. So this is T3, T2, T1, P. This is where we've arrived. Okay? Now, let's think about this same thing, but the other way around. There's a point P, and it's not our vantage point that's changing, it's actually P that's moving around. And in this case, we're applying the same chain of transforms, but this time we're going right to left. So this is point P, 2, 2, expressed in our original So this is point P, 2, 2, expressed in our original coordinate frame. And now our vantage point stays put. We don't move. It's point P that moves around. How does it move? Well, first we apply T1. There's no rotation. We just move P by 2 units along X. Okay, we've moved it. What's next? Then we apply T2. There's a rotation by 100 degrees around Z, but again, careful. Our vantage point hasn't changed. We are still right here. So it's this Z-axis right here that P is rotating around. So then if we rotate around this axis right here, P is going to do all this big circle and land at the opposite side. Okay? So we have now done T2. We've rotated P by 180 degrees around Z. That's what it's ended up. Now we're going to apply T3. T3 means a translation by 2 along Y. Again, our vantage point hasn't changed. The Y-axis still points up, so this translation is going to be up along the Y-axis. This is where P ends up, right? So P has started off right here. It moved here, then it moved here, and then it finally moved up and ended up right there. And now, if I put all of this on a single slide, it's a little busy and hard to see, but you can obviously see that we've ended up at the exact same spot in both cases. Okay? So we can reason about this as, hey, we go left to right, we start with nothing, we start with the identity, but then our vantage point keeps changing. We do T3, our vantage point has jumped somewhere else. We do T2, our vantage point has jumped again. We do T1, again our vantage point has changed, and now we observe point P. This is where it is. The other way to think about this is we start with point P in our one and only coordinate frame. Our coordinate frame never changes. Okay? This is point P, so now we go right to left. We apply T1 to P, it's moved over here. Then we apply T2. Our vantage point never changes, so it rotates around our Z, it moves all the way here. And then we apply T3, which brings P up here. Both of these ways of looking at a transform chain are valid, and they are used for different things in robotics. Mathematically, they are indistinguishable. Whether it's your vantage point that changes or whether it's the actual content of the world that moves, mathematically, it makes no difference. Conceptually, though, you should think of it as, hey, either my reference frame is changing or something in the world is actually changing. And in general, when it's the reference frame that's changing, you go from left to right. So if I start off with the definition of my frame, so I start off with an identity as my frame, then I start applying transforms, and I keep moving into new locations. If I start off with something, with a point P, I left multiply. You cannot even right multiply, right? If you have a column vector and you'd like to right multiply with the transform matrix, this cannot even work. The dimensions of the matrices don't work. Yeah. So then you left multiply. You move the point to a new location. You move the result somewhere else. You move it again. Okay? Let's do another example to see that the order of operations also matters. Let's say we have two transform matrices. This is T0. Okay, and this is T1. Does the order in which I apply these matter? So in other words, if I do T0 followed by T1, and if I do T1 followed by T0, what happens? Well, let's try it out, right? T0, we have a translation by 3 and 3 along each of the x and the y axes, followed by a rotation. We can tell that this is 45 degrees around z. So if I do T0, this is my new coordinate frame. I've translated, and then I've rotated by 45 degrees. Then I do T1, which has no rotation. It has a translation by 3 around x. Careful, though. My x has changed, right? I've gone through T0. My vantage point is now different, so now my x is pointing in this direction. So if I move by 3 along x, this is what I end up. So T0 times T1 is that. Now, let's do them in the other order. Let's say I do T1 first, which is the translation along x with no rotation. So that brings me to here. And then I do T0. I move by 3 and 3 each along x and y, and then I rotate. So this is my translation and then my rotation. So this is what I end up. Obviously, I've ended up in a completely different vantage point. So if I do T1 first and then T0, I end up here. If I do T0 first followed by T1, I end up there. And that obviously makes sense. Matrix multiplication is not commutative. So these are not the same. Okay? So now, let's say I observe a point P at coordinate frames 1, 1, and with 1 being the third frame. Then T0, T1, P is going to be starting from here, going to coordinate frame 1, 1, so somewhere here maybe. Okay. Whereas if I do T1, T0, P, then I start from here, and I go up a little bit, so maybe somewhat like here, completely different point, right? So, when chaining transforms, the order of operations matter, and any transform and any point gets applied in the new vantage point that's defined by whatever is to the left of it. So in this case, T1 gets applied in the vantage point of T0, which is to the left of it. P gets applied in the vantage point of T1 and T0, which are both to the left of it. And here, T0 is applied relative to T1, and then P is seen in the vantage point defined by T0, in turn defined by T1. So order matters, and always think what coordinate frame you are in right now when you are applying a new transform.